In this lab, we're going to be doing acid-base titration curve modeling using Microsoft Excel. In part 1 of the lab, we'll model the titration of a strong acid with a strong base. In part 2, we'll model the titration of a weak acid with a strong base. And in part 3 of the lab, we're going to insert your data from the pH titration of an unknown organic acid, and we're going to fit your data to the theoretical weak acid strong base titration curve. A little bit of preliminary background. So typically, if you had to do an acid-base titration curve in lecture, you would be given the volume of acid, you'd be given the concentration of acid, and you'd be given the concentration of base. And then you'd be asked to calculate the pH for any given volume of added base. So we'll be given VB, and we got to calculate pH. So you know from our previous lectures that the shape of an acid-base titration curve looks something like this. And the first thing that you wanted to do in that process is to determine where the equivalence point volume was. The next thing you would do is you would write the titration reaction, and then you would do the before and after mole stoichiometry. And then the third step of that process was you would find out what's left over after the titration reaction has completed, and you would solve for the pH accordingly. This is the step where it got a little tricky, because it depended where you were on the curve how you would solve. If you were back here at the origin, you had only weak acid, and so the way you would solve was to do a Ka equilibrium. Set up your ice chart, solve for X, and that would be hydronium ion concentration, then take the minus log to get the pH. If you were somewhere in the buffer region here, between the initial volume and the equivalence point volume, you would have neutralized some of your HA, but you'd still have some left over. And when you neutralized it, you make some A minus. So you have a mixture of HA and A minus, which is a buffer. And the way to solve for the pH is to use the Henderson-Hasselbalch equation. pH equals pKa plus log of A minus over HA. If you were at the equivalence point, you would have exactly neutralized all your HA with your hydroxide, and you'd only have A minus in there, which is a weak base. The way to solve for the pH of a weak base is to do a Kb equilibrium. Set up your ice chart, solve for X. X will be hydroxide, then take the minus log to get the pOH, and subtract from 14 to get the pH. Finally, if you were anywhere past the equivalence point, you will have neutralized all your HA to make some A minus, but you'd also have some extra hydroxide left over. Since A minus only dissociates partially, and hydroxide is a strong base, dissociates 100%, the hydroxide will dominate the pH here. You just have to find out how much is left over, take the minus log of that to get the pOH, and then subtract from 14 to get the pH. So this is one of the disadvantages of generating your pH curve this way, is that you have to solve the problem differently depending on where you are on the titration curve. So in today's lab, we're going to take a different approach. So you'll still be given VA, CA, and CB. But this time we'll be given the pH, and we'll be asked to calculate the corresponding VB. So we're coming at the problem from the exact opposite approach. Let's say that we're doing this for the titration of a strong acid, HCl with sodium hydroxide, to make water and NaCl. Using this approach, we're going to use the method of charge balance, which is why I wrote the titration reaction not in the ionic form, but including all the ions. So we want the total charge on all of our cations, so n moles of sodium plus n moles of proton, to equal the total charge on all of our anions, so n moles of chloride plus n moles of hydroxide. Now the number of moles of sodium is going to be solely dependent on the amount of sodium hydroxide that we added. So this is the same as the volume of our base times the concentration of our base. The number of moles of proton, on the other hand, will depend on the pH. So that'll depend on the total volume, Va plus Vb, times the concentration of hydronium ion. And we would get that concentration of hydronium ion from 10 to the minus pH. The number of moles of chloride is solely dependent on the amount of HCl we had present initially, which is the volume of our acid times concentration of acid. And finally, the moles of hydroxide will be equal to the total volume, Va plus Vb, times the concentration of hydroxide ion. And we would get that from Kw over H plus. Remember, we know H plus from 10 to the minus pH, because the pH was given in this case. So here we have our principle of charge balance in terms of concentration of proton, concentration of hydroxide, initial concentrations of acid and base, and the volumes of acid and base. Our goal is to find the volume of base for any given pH. So we're going to try to solve this equation for Vb. So first we'll collect all the Vb terms together on the left side. So we have Vb times Cb plus proton minus hydroxide when we bring that over from the other side. Then we'll collect all the Va terms on the right. So we have Va times Ca plus hydroxide and then minus H plus when we bring that over from the left side. All right, to solve for Vb, we got to divide both sides by the quantity in parentheses on the left. So that gives us Va times Ca plus hydroxide minus H plus divided by Cb plus H plus minus hydroxide. So for the first part of the lab, where we're modeling a strong acid with a strong base, this is the master formula that we're going to use to calculate the volume of base that is necessary to get to any given pH. So in our modeling of this titration curve, we're going to start at the pH of our acid, which we can easily calculate from minus log of the concentration of acid initially, since it's a strong acid, and we're going to end at pH of our base minus 1 pH unit. We can easily calculate the pH of our base because we know the concentration of base initially. Minus log of that will give us the pOH, and we can subtract from 14 to get the pH of our base. So we'll take that range of pHs and we're going to divide it into 100 evenly spaced pH points, so that we have 101 total data points, 101 total pHs. And we're going to calculate the volume of base at each of those different pHs using this master formula. Obviously, if we had to do this by hand, that would be 101 calculations, which would be a big pain in the butt. However, we have Excel where we can easily put some of these units, Ca, Cb, etc., in the top of our spreadsheet, and then we can have a column for the pH and another column for the volume of base. We just type our formula in for the volume of base calculation, click and drag it down the whole column of VBs, and boom, Excel will have calculated all these values in less than a second for us. And then we can graph them onto our acid-base titration curve. So in the first part of the lab, we're going to do that. We're going to graph what the shape of a strong acid, strong base titration curve looks like. Then we're going to take our column of pH and VB that we have in the left side of our spreadsheet, and we're going to copy paste them over here somewhere in the right side of our spreadsheet. But when we do this, we're going to paste special. Many of you probably have never done paste special in Excel before. So over here in this column, we have our pH values and our VB values, and these were calculated values. So they depend on all the things that we put in the top of our spreadsheet, what the concentration of acid is, what the concentration of base is, what KW is, etc. But when we paste special as values over here, we're now going to take that data, which was based on our formulas, and we're just going to have that data as actual numbers or actual values. Okay? So it won't change if we change any of the boxes in the top of the spreadsheet. However, this pH and VB over here on the left will change if we change some of the boxes in the top of our spreadsheet. So then we're going to copy paste these data onto our graph so that we have two curves that are superimposed right on top of each other. And then we'll begin to ask ourselves some what-if questions. What if we change the concentration of our acid? So that's easy enough for us to do. We'll go to the top of our spreadsheet, and where the CA box is, we'll just type in a new concentration. All of the data that's over here on the right side of our spreadsheet, which is one of these two curves, is going to stay where it is. But all this data on the left side of our spreadsheet is going to change as we change VB. And that will change the shape of our curve, right? So our two curves will not be superimposed on each other anymore. One of them will shift in one direction, either to the left or the right, depending on whether we increase the concentration of Ca or decrease the concentration of Ca. And then what we can do is we can write down what happened. Okay, our Excel spreadsheet has moved the curve to the right when we change Va, and we increase the concentration of Ca rather, then the volume that it takes to reach the equivalence point obviously is going to have to increase. And we'll draw this change in our report. Then we'll go back to the original value of Ca and we'll change something else, like maybe Cb, and we'll see what happens. We'll keep doing this until we've answered all of the what-if scenarios that are presented to us in the first part of the lab. Alright, so here we are in part 1 of the lab where we're modeling a strong acid, strong base titration curve. In this part of the lab, we're going to model the titration of 0.05 molar HCl, 50 milliliters of that, with 0.10 molar sodium hydroxide at 298 degrees Kelvin, so that our Kw is 1 times 10 to the minus 14. I've already set up the Excel spreadsheet in the directions with my name, the pH of acid, pH of base, pH of stop, pH increment, etc. Now I'm going to fill in the formulas for you. So in cell C2 here, we want to type the formula to calculate the pH of our acid. Since it's a strong acid, it's simply equal to negative log of our acid concentration. So we type in equals negative log and then parentheses, and then we can either type in A4 or we can click on cell A4, which is our concentration of acid. Close our parentheses and then hit enter. And you see that it's calculated the initial pH, 1.30. Then in cell D2, we're going to type in the formula for calculating the concentration of, or the pH of our base. So this would be equal to minus log of H plus, where H plus is equal to Kw over hydroxide. Minus log of Kw over hydroxide is the same as plus log of Kw hydroxide. So we can simply type in equals log, okay, and then our concentration of base divided by our Kw, and hit enter. And there's our pH of our base. In cell E2, we want to say that we're going to stop our titration at a pH that's equal to a pH of our base minus 1. So D2 minus 1. And then our pH increment is going to be that whole range of pH from pH acid to pH stop divided by 100. So equals E2 stop minus C2, where we start, divided by 100. Okay, next we're going to go down to under the dose numbers here. So we wanted 101 data points. So we'll start with dose 0 and then dose 1, and we want to go all the way down to 100. So you can stop here after 0 and 1, and you can highlight these two cells. And then you can come down here to the lower corner where you get that plus sign. You can click on there and drag it all the way down. To cell 107 there. And you can see that it automatically fills all of those in for you. So it recognizes the pattern that you had put in the top, and it continues that pattern all the way down. Next, we're going to go over here to the pH column, and we're going to type in the formula for calculating the pH for a given dose or a given data point on our curve. So we want this to be equal to our starting pH, which is in cell C2. Now, when we copy paste our formula, if we don't want it to change the value of this particular cell, we have to use our $ formula in front of it. So we do $C, $2, and then this will be an absolute reference. It will always refer back to that cell, and it won't change the C and the 2 when we copy paste. It'll always keep C and 2 in there. So we'll always start with that pH in $C, $2. And then we're going to add to that the increment, which is in $F, $2, times our dose number, which is over here in cell A7. Now if we click on this and grab the lower right corner, drag it all the way down the column, you'll see that as it calculates one of these cells down here, it hasn't changed my starting pH of the acid or the value of the increment, but it has changed the value over here to our dose number. So these are called absolute references, the one with the $ symbols. And this is called a relative reference because that one changes as I copy paste. It is relative to the cell that I pasted into. Okay, so now we have all of our pH values from our starting pH of our acid to our stop pH of 12. And the next thing we want to do is we want to calculate the concentration of proton and put that in column B here. So we know that the concentration of proton will be equal to 10 to the minus pH. So we type in the formula equals 10, and the caret to indicate to the, and then minus, and we click on our box over here for the pH. This we want to be a relative reference, not an absolute reference. Next we'll calculate a formula for the hydroxide concentration, which will be equal to our Kw, which we want to be an absolute reference, so $D, $4, divided by our proton, which will be a relative reference. And then we hit enter. Alright, next we're going to put in the formula for VB, which we had derived earlier. So remember that VB is equal to the quantity VA, which we want to be an absolute reference, so $C, $4, times, Excel does not understand that if we just put parentheses in there, it'll mean times. We have to put the times symbol in there. And then the quantity, Okay, CA, which we want to be an absolute reference, $A, $4, plus hydroxide, which is a relative reference, and then minus proton concentration, which is also a relative reference. Close that parentheses, and then we're going to divide by the quantity, so open parentheses, CB, which is an absolute reference, $B, $4, plus proton, which is a relative reference, and minus hydroxide, which is also a relevant reference. Close our parentheses, and then hit enter. And the correct value should be 6.67 times 10 to the minus 11. Now we want to drag all these formulas down. We can use the shortcut and just select all three of them, go to the lower right corner to get our plus symbol, and then we can drag them all the way down to cell 107, row 107. And your value should look like this. Okay, now that we have all of our formulas in there, we want to format some of our columns for the correct number of sig figs. So we want our volume and our pH here to go to the 100th decimal place. So we can highlight all of those numbers all the way down the column. And then we come over here to format, and we can set this to either number or scientific. If we do it to scientific, that'll work even when we have really small numbers. Then we can tell it how many decimal places to display. So we want to keep it right there. Incidentally, when you format the columns in an Excel spreadsheet and then you use those columns to make a graph, it will automatically format your axis labels on the graph to having the correct number of sig figs as well. Okay, so next we want to graph VB versus pH. So we'll highlight VB versus pH, all those cells, and then we're going to do insert, and we want to choose a scatter plot. We don't want to connect the dots. Okay. And then it tells us in the directions that we want to move this graph so that it fills the space between F3 and K40. So F3 is up here and K40. So we're going to have to drag this corner here and lower it down to K40 here. Where is K40 at? Right around here, I think. K40, like that. And we should put some axis labels on here. So add chart element, axis title, primary horizontal. We'll type in VB, units of milliliters. And then add chart element, axis title, vertical. We'll type in pH and enter. So what we have right now is we have a graph of our strong acid, strong base titration curve. Okay. Now they're going to want you to print this out. So the next thing we're going to do is we're going to set our print area. So I think that's under the file menu. No. Maybe it's under page layout here. All right, let's first make our orientation of this graph to be landscape, and then we want to set our print area after that. So we're going to have to highlight the area that we want to print. So from A1 down to K40, say. And then we can go to print area and set print area. And so now it will print just that region of the graph that we have highlighted. Okay, at this point, you can save your spreadsheet. And tell it, of course, where you want to put your spreadsheet. Give it a name, strong acid sim. Okay, so we've done our strong acid sim, but there are some post-lab questions there where they want us to play with this acid-base titration curve. So what we're going to have to do next is we're going to change some of these concentrations of our acid or base, etc. And we're going to see how that changes the shape of our titration curve. So to answer these what-if questions, we're going to take the data that is in columns D and E, our volume and pH data. We're going to highlight that data. Okay, then we're going to do copy. So I do that with Control C to copy. And then they want us to come over here somewhere to the right of our graph, maybe in column L and M, and we're going to paste special. So to paste special, we come back to the home menu, paste, and then we want to come down here and do paste values. Okay. So what this does is now over here, we only have the numerical values in this column. But over here, we still have the formulas. So if we change any of these boxes up at the top of our spreadsheet, the values in columns D and E will change, but the values in columns L and M will not change. Okay, so we'll take the data in columns L and M, and we'll highlight that. Then we'll do copy, so I do Control C. And then we want to put that on our graph. So we'll click somewhere on our graph here. And then we want to paste special again. Paste special from the paste menu. Okay, we want to add our new series in columns, so that's the default value. We want to check the box that says series names in first row, and we also want to check the box that says categories X values in first column. Then we click OK. So you can see that the color of my graph has changed. I actually have a blue graph and a red graph that are currently of the same data values, because the values in columns D and E are the same as the values in columns L and M, and they're both superimposed on one another. Alright, so the first what-if question that we have to answer as part of our post-lab is what happens if we change the concentration of our acid from 0.050 to 0.052. So all I got to do is come up here and change that from 0.050 to 0.052. Hit enter, and you can see what happened to my graph. My graph has moved so the red data, which is my original data, is still here where it was before, but all of the blue data has changed because I changed that concentration of acid. So we would draw on our report form the shape of these two curves, and then we draw an arrow from the red pointing toward the blue, showing that what happened is our equivalence point volume has shifted to a larger volume because we increased the concentration of our acid. And then we make some kind of comment on the picture as well in our notebook so we know what happened. So that was our first what-if question. After each what-if question, you go back and you change it to the original value. So we go back to 0.05. The second what-if question asks what happens if we change the concentration of our base from 0.1 to 0.105. All right, so we just type that in and we see that now the curve has shifted to the left. So we draw an arrow from our original red pointing to the left to our blue. And we say the equivalence point volume now has shifted to a lower volume because I increased the concentration of base. That all makes sense. All right, we're done with the second post-lab question. Change that back to 0.1. The next one says, okay, what happens if we change both the volume of our acid from 50 to 5 and the concentration of our acid from 0.05 to 0.5. So we have the same number of moles of acid, but we have different concentration, different volume. You can see that our equivalence point is the same in this case, but that our range of pH has increased. So you would draw that on your post-lab and comment on it. And we'll go back to our original values again, 0.05 and 50. Our fourth what if question is what happens if we change the KW. You say change KW, but KW is a constant. Yes, but equilibrium constants depend on the temperature. And so the value of KW at 298 is 1 times 10 to the minus 14. But the value of KW at 100 degrees Celsius, or 373 Kelvin, is equal to 5.4 times 10 to the minus 13. We type in 5.4 and then E minus 13 to indicate that. And you can see what happens is I have the same equivalence point, the same starting pH, but my ending pH is at a smaller value. Right, and that was my fourth what if question. Go back, change that to 1E minus 14. And then we'll do our final what if question, which says, what if we titrate 50 milliliters of 0.0005 molar? So we make this 100 times more dilute, but we also make our concentration of base 100 times more dilute, so 0.001. And then we sketch the shape of the original versus the new, and you can see that the range of pH values is smaller, but we have the same equivalence point volume. And we comment on that. So we've now done all 5 what if questions, and we go back to all of our original values here. Okay? And if we haven't already, we save our spreadsheet. We have already saved it, so we shouldn't have to do it, save it again at this point. All right, now we're ready to begin part 2. I have to give you a little bit of theory background first on part 2 before we can do that. So let me try to get out of here.